Chapter 2, The Chemical Basis of Life. Why do we study chemistry in our A&P class? Chemistry is the study of body functions that depend on cellular functions, and when you talk about cellular functions, these functions result from chemical changes. Biochemistry helps to explain physiological processes and help develop new drugs and methods for treating diseases. Chemistry is the study of the nature of matter. This section includes the study of composition of substances, changes that occur in substances, and substances that make up structures in living organisms. Chemical reactions underlie all physical processes. Some of these functional chemical changes produce energy. And what is energy? It is the capacity to do work, and is what we use to do work. An example would be an ATP. It is stored in the bonds of the energy is stored in bonds, chemical bonds in an ATP molecule. As the ATP is broken down to ADP plus a phosphate, energy is released. Then in cellular respiration, that ADP and phosphate joins back up together in a very complex series of reactions, and you have the potential energy in that ATP molecule. Is very important. It's like our energy currency. Let's look at the structure of matter. Matter is anything that takes up space and has weight or mass. It is composed of atoms. Solids have a definite shape and a definite volume. We can actually weigh them, measure them. They keep their shape and have a definite volume. Liquid has a definite volume. We can measure it, but indefinite shape. It takes up the shape of the container. A gas has indefinite volume and indefinite shape. In other words, different volumes and different shapes depending on the container it is found in. Now, if you go down here to the filling station and get your propane tank refilled, they deliver that propane under very high pressure, and it liquefies that propane so that they can measure it. And if it were a gas, as they filled that tank, it would be harder to measure it. Now, there is a third type of matter, and it is only found on the sun, so it's not important to us here. It is important to us because we depend on the sun for heat and photosynthesis and things like that. But that fourth state of matter is plasma, and we don't have that. We do not see plasma, that state of matter, on the earth. And all matter is made up of the smallest particle of matter, atoms. And let's look at atomic structure. Atomic structure, the atoms are composed of subatomic particles. In the nucleus of the atom, this area right here, the nucleus of the atom, we have protons. There's another proton. There's another proton. They carry a positive charge, so we have this little plus sign here that tells us that these are positively charged particles found in the nucleus of an atom. There are neutrons. Neutrons carry no electrical charge. They're neutrals. So that's a neutron, that's a neutron, that's a neutron, that's a neutron. Okay? Now, that is what the nucleus is made out of, is protons and neutrons. Now, when we get to helium, it only has a proton. We'll talk about that later. Okay, so in the nucleus, protons and neutrons. In an orbit or energy shell, at different energy levels, we have electrons. They carry a negative charge. So for an atom to be neutral, it will have equal number of positive charges to negative charges. So it would have equal number of protons to electrons. And so this particular element, lithium, has 3 protons, and if it is neutral, it is going to have 3 electrons. Now remember, the neutrons don't count when it comes to the charge of an atom because it doesn't have a charge. The protons and the electrons cancel each other out in a neutral atom. Atoms tend to be neutral. Can you use a name and the charge of the particles to describe a neutral atom? That would be the number of negative electrons equals the number of positive protons. And can you tell us where those particles are found? Electrons, we just mentioned electrons. They are in an orbit around the nucleus of an atom. Here we have 2 electrons in orbit around the nucleus of this helium atom. This particular type of drawing is called a planetary model with those electrons in orbit. And this is called an electron cloud model. Now what's interesting about electrons is they're very minuscule. They're very, very small. So it's very difficult to see an electron because when we use enough magnification, we can see the cloud that electron makes in its orbit around the nucleus of this atom. So the electron cloud is basically what we see. It is extremely difficult because they're so small and they're always in motion to see an individual electron. Electrons are found in regions or spaces called electron shells, energy levels is where we would find electrons. Each shell can hold a limited number of electrons. For atoms with atomic numbers of 18 or less, the following rules apply. The first shell can hold up to 2 electrons. So here we have hydrogen. It has 1 proton and 1 electron. It's a neutral atom. By the way, it has no neutrons in its nucleus. This 1 electron will revolve around that proton. Now here we have helium, and it has 2 electrons in its outer shell. And then lithium with 3 protons. For it to be neutral, we're going to fill this electron shell, and then its 3rd electron would be in a second orbit. The second shell can hold up to 8 electrons. The 3rd shell can hold up. The 3rd shell holds up to 8 electrons. The lower shells will fill first, just like this one is full, and then that 3rd electron goes to the next energy shell or electron shell. If the outermost shell is full, the atom is stable. Now, hydrogen here only has 1 electron. This outer energy, this orbit here is not full. This electron shell is not full, so this makes hydrogen extremely volatile. Helium is inert. It's not volatile because its outermost shell is full. Lithium is also very volatile because its outermost shell is not full. If the outermost shell is full, the atom is going to be what we call inert or stable. These electron shells or orbits follow the octet rule. This only works with the first 18 elements, and these include the elements, most of the elements that are important to living organisms and their makeup and chemical processes. Bonds will form when two or more elements combine. Their ability to bond with other atoms joining to form a compound, is dependent upon these outer shells of electrons. The chemical reactivity, the bonds are dependent on the outermost shell and the electrons found there. They're also called, this is also called, valence electrons are found in a valence shell. Atoms will react to fill this outermost shell. If an atom has 3 or less electrons in this outermost shell, it will tend to give them up to become stable. Hydrogen is very volatile because it tends to give the electron up very easily, and but with this electron it's very volatile. That's why we make hydrogen fuel to fuel the rockets that we send to space, because we can use hydrogen fuel because it's very volatile because of that one atom in its outermost shell. One electron in its outermost shell. That electron, and given off of that electron, is very easily done by hydrogen, and so hydrogen's very important to us. It gives this electron up freely, and you will not find this in nature. You will not find a single hydrogen atom in our atmosphere. You'll have 2 hydrogen atoms that form sort of a figure 8 in the orbit of the electrons around when they form a bond, and that makes them stable. If we had this in our atmosphere, a single atom of hydrogen, our atmosphere would blow up because it's so volatile. H2 is what we find in our atmosphere. O2 is also what we find in our atmosphere because these are not volatile. More than 4 electrons in that outermost shell tend to gain electrons so that it fills that outermost shell. Now, if the shell is full, I mentioned this just a minute ago, but if that shell is full, like helium here, it is called inert, I-N-E-R-T. Now here we have a periodic table, and in this periodic table we can see hydrogen here. We see its chemical symbol, which is a capital H. And right here we see a 1s. Okay, we see the chemical symbol for our abbreviation for hydrogen. In this corner of this square is going to be the atomic number. Okay, right under the name for the element is going to be the atomic mass. Now, the atomic mass is also called atomic weight. Now, this particular key to this table says atomic weight here, and your textbook will say in one place atomic weight, and another place it may say atomic mass. What's the difference? Well, when we say weight, we're usually referring to the amount of pull gravity has on our body or an object. When we get up on the scales, it's our body. Mass is the amount of matter in an object. So really, mass is a little better term than weight, but weight is used very frequently. So here is the atomic element symbol. There is the name of this element, its atomic number, and right below the name is the atomic mass. Now this is a very detailed periodic table. If you were in chemistry, this would be a good thing to know. A lot of different information here that we're not concerned with in this class. The most important thing you need to remember is the atomic number. Sometimes it's here and sometimes it's centered. The atomic element symbol and the element's name and the average atomic mass. So over here, here's helium. We looked at helium just a few minutes ago. And helium, its atomic number is 2. Its atomic mass is 4. Its symbol is H, capital H, little e, and its name is helium. Okay, the atomic number. Now on the periodic table we just looked at, this atomic number was over in this corner. So you're going to see different types of periodic tables. Just be aware of that. And for this symbol, or this periodic table, your atomic number would be more centered. So the atomic number is 11. The element symbol is capital N, little a, and this is sodium. The atomic number is the number of protons in the nucleus of one atom. Each element has a unique atomic number, so this is not going to change. If this atomic number changes, it changes the element. And it would take extreme amount of energy, like a nuclear bomb or hydrogen bomb or a fission or fusion, that would release a tremendous amount of energy or take in a tremendous amount of energy to change this to a different. Under normal circumstances, it just would not happen. Okay, it equals the number of electrons. Here's the key thing here, in a neutral atom. Remember, in a neutral atom, you'll have equal number of protons with number of electrons. Okay, so in the nucleus of the atom would be 11 protons, and in orbit, remember we talked about the energy levels, the shells. Here on this particular periodic table and this particular element, it gives you the electrons in each energy shell. So remember, the first energy shell is full when it has 2 electrons. But we have to have 11, so the next shell will be full after 8 electrons, and then a third energy level, or the valence shell with its valence electron, would be 1. So 2 plus 8, 1 more. So what does this say about sodium? it's going to be extremely volatile because it has this one electron in that outermost shell. So sodium, if it's exposed to air, can blow up. Now the atomic weight is the number of protons plus the number of neutrons in one atom. The electrons do not contribute to the weight of the atom. Remember, because I said they were so minuscule, it does not contribute to the weight of the atom. All right, so atomic number is the number of protons. The atomic weight is the number of protons plus the number of neutrons. So the atomic number here gives us the number of protons, 11. And here is the average atomic mass, or weight. Okay, so we could round this off. And so that would be 23. So we know that there are 11 protons in the sodium nucleus. Okay, the atom's nucleus. 11 protons, and then the atomic mass is 23. I'll round it off. The number of protons plus the number of neutrons is the atomic weight or mass. All right, so if we know there's 11 protons and the atomic mass is 23, how many neutrons would there be? How do you figure that out? Well, just subtract 11 from 23. And what is your answer? Oh, 12. So there's 12 neutrons in a sodium atom. There's 11 protons, 12 neutrons, and its atomic weight, add those two together, round it off, would be 23. And if this is a neutral atom, it's going to have 11 electrons and 11 protons. But know how they break down into the different energy levels or shells or orbits. 2 is full in the first energy shell or orbit. Then the next bit of electrons goes to the second level, which is full at 8, and then the third level, you have a single electron in that third level. Again, that makes it very, very volatile. So can you tell me the atomic weight of an element whose atom contains 6 protons, 6 neutrons, and 6 electrons? Atomic weight is going to be 12. Remember, electrons do not contribute to the weight of the atom. Electrons do not contribute, so the atomic weight is the protons plus the neutrons. How about 4 protons, 4 electrons, and 5 neutrons? Yes, 9. Because there were 4 protons and 5 neutrons, and that's a total of 9. 4 electrons are minuscule and they do not contribute to the weight of the atom. What about 7 protons, 7 electrons, 7 neutrons? 14. How do you get the atomic number? Yes, the number of protons. The atomic mass, protons plus neutrons. The atoms of 2 kinds of elements are going to have different atomic weights, and they will be of a different size. Okay, in this chart we see information about the atoms such as the atomic number, weight. It can be found on a periodic table. This chart Below is a summary of the first 12 elements on a periodic table. Here's hydrogen. Its atomic number is 1. Its approximate weight is 1 because it only has 1 proton, no neutrons, and its electrons are in the first shell of only 1, very volatile. Helium, the atomic number is 2, approximate weight is 4, so that would also be 2 protons, atomic number, the number of protons and the number atomic number is going to be the same. So 2 protons, and because it's neutral, 2 electrons in orbit around it. That first energy level's full, so we call that inert, very stable. And it's also going to be very difficult or impossible to form a bond between this helium atom and another atom because its outer valence shell is full. Okay, its atomic mass is 4, so we have 2 protons and 2 neutrons. If we didn't have this column right here, you could tell me these numbers because you know the number of protons and you know the atomic weight, and you just subtract. But if I gave you the atomic weight and the atomic number, you should be able to give me the number of protons, subtract that from the atomic weight, and that would give you the number of neutrons. Skip down here to neon. Here is its symbol. There's the element name, its symbol. Its atomic number is 10. Its atomic weight is 20. I can subtract 10 from 20, and I know there's going to be 20 neutrons. The atomic number is 10, so I know there's going to be 10 protons. Subtract that 10 from the 20, there's going to be 20 neutrons. Its first shell is going to be full at 2, and its second shell is going to be full at 8, and here's another inert element, not reactive, so we can safely have neon lights and not worry about those tubes exploding. And here's sodium. It's Na, it's its atomic symbol. Its atomic number is 11. Its approximate weight, 23. We looked at this just a minute ago. So since its atomic number is 11, we know it has 11 protons. We subtract the atomic number, or the number of protons, or the number of protons from the atomic weight or mass, and that would give us the number of neutrons. Now it has 11 protons to be neutral. It would fill its first shell with 2 electrons, the second shell with 8 electrons, and then 1 in its outermost or valence shell. And this makes it extremely volatile. Yes, it explodes when it is exposed to air. Magnesium is very volatile also. Atomic number is 12. Atomic mass is 24. So 12 protons, 12 neutrons. First shell 2, and then 8 in the second shell, and 2 in its third or valence shell.